several topics, and in my talk I have to concentrate in one of those. So continuous model theory is a model theory of metric structures. This is a classical subject which was started by Chang and Kiesler in 1966. And my aim is to show that category theory can be used in such continuous model theory. And I will concentrate on Banach spaces. So in ordinary model theory, an important concept is that of countably saturated model. This is a countable model which is injective in the usual sense with respect to embeddings of finite models. So it means that for any finite model and for any embedding of domain, it can be extended to embedding of codomains like that with triangle commutes. And this can be constructed by a small object argument. And in model theory, it's also called Fresnel limit. This is not limit, it's a co-limit, but this is just this. Countably saturated model is called a Fresnel limit of finite models. It has a remarkable property, this countably saturated model, that it contains any countable model as a submodel. So one can say that it's universal countable model. To get it from this injectivity is easy because you express your countable model as a union of a chain of finite submodels, starting from the empty one, and then use this extension property along this chain, and then you get the embedding of your countable model to this finitely saturated model. Now, switching to Banach spaces, so then finite models are replaced by finite dimensional Banach spaces. Countable model by separable Banach spaces, which mean those which have a countable dense subset. Very soon I will reformulate it using concepts of category theory. And as embeddings, one takes isometries. It means linear maps which preserve distance. But that's well known that there is no separable Banach space which is injective with respect to isometries between finite dimensional Banach spaces. Which means that if you run the small object argument, it doesn't stop at Rf0, you have to go up to Rf1, so then this your saturated model is not countable, it's not separable, but has, in fact, it corresponds to Rf1. So you don't have nothing of this countably saturated model in the standard sense. But Gurari in 1966 constructed a separable Banach space G, which is approximately injective with respect to isometries between finite dimensional Banach spaces. So just it is this classical definition, but instead of injective, one takes approximately injective. So what does it mean? But maybe before telling you what does it mean, maybe I have forgotten to say that what I am reporting now is in fact based on a joint research with Walter Tholen and a later research with Jiří Adámek, and I will end with something which goes beyond that. And also at the end of my talk, I will give you references which I mentioned. So, but let's come back to this basic definition of approximate injectivity. So it means that if you have any isometry H between finite dimensional A and B Banach spaces, and any isometry from A to G, then it can be extended to an isometry from B to G, but not such that this diagram commutes, but it commutes up to epsilon. What does it mean to commute up to epsilon? It means that the distance of F and the composition G after H is not equal, but has distance less than epsilon, or less or equal to epsilon, and distance where, now in the metric space of all morphisms of Banach spaces from A to G. Well, you will see soon that it makes sense because Banach spaces are enriched over metric spaces, but this can be phrased in that way that for any element in A, the distance of images of those two things is less or equal to epsilon. So this one can say this is the analytical concept of approximate injectivity. And the result of Gurari was that indeed that's a separate Banach space, which has this property that's only approximate injective. And a consequence of this is that this separable Banach space is universal separable Banach space. It means that any separable Banach space is a subspace of that one. This is not clear at all because now one has only things which are approximate and now you want to have a real embedding, but this is also related to the fact that it was not clear immediately that this Gurari space is unique up to isomorphism. It's unique up to something which is approximate. It comes out from definition, but it's not clear it's unique up to isomorphism. And that was proved at first by Rosický by deep Banach space techniques, and later, much later, an elementary proof was given by Kubish and Solecki in 2011. And in fact, this argument they used can also produce the fact that this Gurari space is universal separable Banach space. So now my aim is to show that all this can be put in the context of enriched category theory by means of approximate small object argument. So now, what's the basic category theory? So our base category is the category of complete metric spaces. We have to allow distances infinity because otherwise we wouldn't have products, coproducts in this category. And as morphisms, we take non-expanding maps. It means that it cannot increase distance. This category is symmetric monoidal closed. Tensor product is on the Cartesian product, but one takes plus metric. Cartesian product has submetric. And this left adjoint, the internal home, this is what I used just before. It takes this all non-expanding mass from X to Y, this submetric. You have this formula here. Moreover, this category of complete metric spaces is with this factoration system dense isometric. And now the category of Banach spaces, morphisms are linear maps of norm more equal to 1, is enriched over complete metric spaces. And now, if you read this definition of approximate injectivity I gave you above, so it's the same thing that the induced morphism, if you have this H from A to B, so then for any morphism from B to G, you have the composition. And this should be dense. Yes, just if you just look at the definition, it shows that by these extensions, we can come arbitrarily close to F, which means that given F here in the image from A to G, so we can come, because this is dense, so we can come approximately near to this. Which means that this approximate injectivity is in fact enriched injectivity in the sense of Steve Lack and me, which means that in usual injectivity, you want that this induced thing is surjective. If usual injectivity oversets, this means that this is injective. So here, one replaces surjections by some class of morphisms, by dense morphisms, and wants that this thing is dense. So this is one thing, that this analytical concept of approximate injectivity can be replaced by just a categorical concept of injectivity and this categorical concept. This category complete metric space is locally L1 presentable as a closed category, and L1 presentable objects are separable spaces, with those having dense subsets of connectors more equal to L0. It's not locally finitely presentable because the only finitely presentable object is the empty space. And similarly, Banach spaces are locally L1 presentable, separable spaces are L1 presentable objects, and again, there are no finitely presentable objects except the trivial one. So now if you have a small object argument and you want to show that it converges, you want to stop it. So then you need that this small object argument is over respect to some morphisms. So you need that these domains and codomains in these morphisms can stop this argument. And usually one uses finitely presentable for that. And here we say that Banach space is approximately finitely generated if his home factor preserves directly limits of isometries. So this is basically the standard concept of finitely generated enriched over metric spaces, complete metric spaces. And why is approximately here? Because what does it mean? It means that whenever you have a directed colimit of isometries and a morphism from A to the directed colimit, so then for every epsilon, that's something wrong here. That's for every epsilon, that's a factorization that comes up to epsilon. So F forgot to here a quantifier that the directed colimit F. Then for every epsilon, there is G such it commutes. Again, it means because to preserve the colimits, it means this comparison morphism is dense. So this dense is that any morphism to K can be approximate, can be arbitrarily closely obtained by factorization through this colimit. And the basic result is that finite dimensional Banach spaces are approximately finitely generated. This result is deeper than one would expect, because if you take this G, if you take this F from A to K, so one immediately feels that it has to be some kind of factorization because this A is finitely dimensional. So you take its base, you factorize this morphism for its object from elements from this base arbitrarily closely following this colimit, and then you extend it. But the problem is that this extension doesn't need to have norm small or equal to 1 because the norm should be close to 1, but also maybe it could be above 1. So that's the problem, because one can get G which doesn't work. And in fact, if you do the same thing in complete metric spaces, these finite spaces, then it's not true, because one can just show that this approximation you get is always from above. So it doesn't work in the category of non-expanded maps. It doesn't happen in Banach spaces because basically addition makes the job so you can do it, but it needs some calculations. And in fact, I needed the help of Věslav Kubiš to finalize this proof. Another point here is that this G you get, this factorization, is not necessarily isometric. Having equality here and having this equation, then G is isometry because isometries are left cancelable. But here it's not isometry. In fact, it's something which is called epsilon isometry, and it's another complication, another ingredient of the proof one needs. So we have this basic thing. You have this approximate finite generation, and now one runs approximate solid arguments, but instead of push-outs, one uses epsilon push-outs. So what's an epsilon pushout? Here you have the definition. So you have F and G, and you want to show what's that epsilon pushout. So this is a commutative square which commutes up to, so this is epsilon commutative square, it commutes up to epsilon. So that for any other square which commutes up to epsilon, that's a unimorphism which compares it but strictly. And this combination of, say, epsilon commutation and strict commutation somewhat reminds one weighted colimits. In fact, epsilon pushouts are weighted colimits. And I am grateful to Ivan Diliberti, who was the first one who realized that this definition gives weighted colimit, which is important. So now, usual small argument, this is just a transfinite composition of pushouts. So here, instead of pushouts, you take epsilon pushouts. And now you construct the Gurari space as a countable transfinite composition of pushouts of just one takes, instead of epsilon, just 1 over n, because one is a countable number of things. Also, one is a countable number of things, so one takes only rational isometries, which are enough, and all is between finite dimensional Banach spaces. So, and this construction, which is countable and converges, exactly because finite dimensional Banach spaces are approximately finitely generated. So, which means that if you, again, I repeat, if you do usual small jet argument with finite dimensional spaces, you have to go up to R1. But if you do this approximate one and use the fact that these finite dimensional, which are not finitely presentable, but are finitely approximately generated, so then this approximate argument stops at R0, which gives you this universal separable space. And its uniqueness can be proved by something which is called approximate back and forth methods. So this is the method which was used by Kubish and Soletsky in the paper I mentioned. And the same thing can be also used to prove that this Gurari space is a universal separable space. So this is how to get by category theory this known result. Now let's switch to something which is again known, but goes beyond my joint work with Walter and Jiří. So Laurent takes the category of operators of Banach spaces. So which means it's just the category of morphisms in Banach spaces. And so I would like to play the same game. But here now I don't know whether operators between finite dimensional Banach spaces are approximately finitely generated. What's the obstacle? The obstacle is, so now here you have directed colimit operators. I use notation which reminds you to previous situation, but these are morphisms between Banach spaces. So morphisms between morphisms are just pairs of morphisms such that the square commutes, where these things are isometries. Now, again, another morphism from operator as now, because now one has now, say, isometry between those operators on finitely dimensional Banach spaces. So, and one takes a morphism from S to K, and one wants to factorize it through some k sub I. Just you can do it because you can factorize this up to epsilon in each component, but the problem is that you don't know that the resulting thing is a homomorphism of operators because it only commutes up to epsilon, this thing. So it's only epsilon homomorphism. But in the course of this approximate small jet argument, it can be corrected to a true homomorphism. So without knowing that S is approximately finitely generated, this approximate small jet argument converges. So this means, in another words, it means that I don't know whether those isometries between those isometries of operators on finite dimensional Banach spaces, I don't know. Sorry, I have to say it again. I don't know that operators on finite dimensional Banach spaces are, say, approximately generated, but I know that they behave in this way, maybe not for all the limits, but for those which appear in this approximate void argument. So they are enough finitely generated, so which means that you can get this, you can stop this argument here and you can get this countably saturated operator. Since both projections from the categorical morphisms of Banach spaces have enriched left adjoints, which preserve isometries, so they preserve approximately finitely saturated objects, which means that this universal thing here, in fact, has both projection to be Gurari space, because this Gurari space is unique up to isomorphism, and both projections are Gurari spaces. So in fact, then this universal thing is a universal operator on a Gurari space, which is a result of Garbulinska-Vergin and Kubish about the universal operator of the Gurari space. Just again, just the proof is just done using this technique I introduced. So of course, it would be nice to get something new. So Banach spaces are equipped with projective tensor product, and monoids in Banach spaces are Banach algebras. And I don't know, I think it's not known whether approximately finitely saturated Banach algebra exists. So, like, if you took this operator, so you took this, it works. But now instead of it, you take something very natural, you take monoids in Banach spaces, and then you would like to know whether you can just do the same thing as before. So this is open, and that's, there are no quite some references about this, but before showing them, so this forgetful functor from Banach algebras to Banach spaces reserves vertical limits and isometries.
Can you hear me? Erkan, this is to, please, you have.
Yes, I am finishing in 1 minute, yes.
Okay.
And then it's left adjoint, then preserves this approximately finitely generated objects, which means that free Banach algebras over finite dimensional Banach spaces are approximately finitely generated, but it's not clear whether this is true for finite dimensional Banach algebras. So they have been studied Fresnel limits of C-star algebras. Not much is known for Banach algebras, and the references I mentioned, this is a joint paper with Adame, joint paper with Walter Tollen. This is something about Fresnel limits of C-star algebras, and these are those papers I mentioned during the talk of Garbulinska-Vergin, Kubish, Rosický, and me and Stiglitz. So thank you.
Thank you. There's time for a short question. Is there any? Oh, okay.
Hello, thank you very much for your very interesting talk. I have a naive question. I was wondering whether all those approximate notions could be made strict notions by replacing all, for instance, the category of Banach space with an equivalent, a possibly equivalent category based on non-standard ideas, like I mean, in non-standard analysis.
No idea. You mean to use non-standard analysis in this, yes?
Yeah.
No, I don't have an idea. You think that could be useful?
I don't know. I was just wondering if that would be a direction to a reasonable direction to study the problem. But thank you.
Thank you. Are there more questions or comments? No. What about online? No. So thank you. It's time. Thank you again.